All right, welcome. Good afternoon, everyone. Welcome to the 20th annual symposium here at Messiah. My name is Josiah Moyer. This is my teammate, Josh Mundis, and we are excited to share with you our project, Secure Kenya Prosthetic Knee for Through Knee Amputees through Messiah University Collaborative. So I guess we'll just jump right in here and look at a video that should hopefully give some context and background to our project. Hey there! Do you ever take the time to stop and think on how amazing your body is? Well, capable of amazing feats like running and jumping, one of your body's most important functions is carrying you from place to place. While many people take for granted this seemingly basic function, there are many people who have lost this ability to walk due to lower limb amputations. That's one of the reasons why our team, the Prosthetic Knee team, partnered with Cure International Kajave, Kenya to help design a prosthetic that would give back patients' ability to walk independently. So 4 years ago, Cure International approached our project team with a problem. Their prosthetic designs for their through knee amputees patients were too unaffordable, and thus their patients were seeking out more affordable, yet also more dangerous, alternative operation procedures. They tasked us with designing a new prosthetic design that would be both more affordable and more desirable than their current in-house selection. Of course, this would not be an easy task, but by mapping out the design specifications and developing a plan, this project was certainly within our capabilities as a team.
What kind of factors do we need to think about when designing this prosthetic knee?
Well, there are a few things we need to consider. Firstly, we want to reduce weight as much as possible. Secondly, we need to reduce thigh lengthening as much as we can. Thigh lengthening in this case is the distance between the biological knee axis and the axis of the prosthetic knee. So the smaller we can get that distance, the closer our prosthetic will be to the biological knee in function. Thirdly, cost reduction is imperative to this project, since our main goal is to make an affordable prosthetic. And finally, due to cultural stigmas against plastics and polymers, we will be making the entire knee out of metal.
It is important when designing parts to design them so that they can be manufactured efficiently. So when we build the prototype of this prosthetic knee, we'll be able to make changes to the process to reduce manufacturing time and cost.
I think this just might work. So I hope that video just gave a little bit of the background, some of the requirements that we're working with in our project, and some of the specifications. Now I kind of want to take a turn and look more at what does our actual design look like. I know we had a picture of it in the video, but sometimes you can see the design and say, well, this is a knee, but how does it really look like when it's combined with like an actual prosthetic leg on a patient? So this next visual is looking at the model integration. In the middle here, we have our actual CAD model of our knee design made in SolidWorks, which is our 3D CAD software to make our parts and assemblies. Connected to the top of the model is what we call a socket, which would be connected to the residual limb of a patient. And then connected to the bottom of our design would be a shank, which acts like the lower leg and foot for the patient in a prosthetic. So I hope that gives some context as well. Moving on to the next slide then, we're looking at the knee motion of our design. So that image on the left is looking at the kind of the baseline model of the knee when it's in full leg extension. And then on the right side is an image of the knee when it's in full flexion, when the knee is pulled back. And the design has a full knee flexion of about 110 degrees of rotation. This video then just gives kind of like a real-time look at how the knee moves from full extension to flexion, and then from flexion back to extension. Again, going through that full 110 degrees of rotation. And then, so now that we kind of looked at, all right, what does the knee look like on an actual when integrated with the prosthetic limb? How does it move? How does it rotate? I want to take some time to then jump into some of the more technicalities of the design. I know this image looks at all the different, labeling all the different parts of the design, but I really want to focus on more the sub-assemblies. And by sub-assembly, I mean different groupings of parts that work together to accomplish specific goals in the project. So there are three main sub-assemblies of our design. One of them is called the main housing of the knee, which is composed of these anterior bars up front and the posterior bars in the back. This proximal plate up here, and then this distal platform down here. And these parts work together in the sub-assembly to hold most of the weight of the person and the patient while they're walking. There are also then two other main sub-assemblies of the design, which we named the damping and the locking mechanism, which we'll go into in more detail in the next slides. So starting with the locking mechanism, if we look at this top image up here, we have a full picture of our full prosthetic design. This first circle here outlines what we call the locking mechanism. And there's a SolidWorks image of this down below. And then the second circle here is the locking pin. So how the locking mechanism works, as its name may imply, it's supposed to lock the design at specific rotations in the knees movement. There are holes within the anterior bars here, and then there are holes throughout the locking mechanism here. So when at different rotations, when these holes in the anterior bars and in the locking mechanism are aligned, the locking pin is fitted through them to then stabilize the knee at those positions. And this has several different goals. One of the main goals is to ensure that the patient can use the project or the knee as a peg leg, like if they're walking on uneven terrain, such as rocky or perhaps on the beach, and they don't want their knee to be moving in those positions. That would be one of the purposes. Additionally, it can be used to hold the knee at 90 degrees, so like if the patient is sitting down, it doesn't have to deal with the motion of the knee. And then the last main sub-assembly of our project would be the damping mechanism, which the damping mechanism is fitted in the back of the knee design here for overall prosthetic knee. And then this right side image here, we have the entire sub-assembly, which is made up of 5 different components. The two main purposes of the damping mechanism, one is to provide stability and build up of potential energy during swing. So when the knee is brought back from extension to flexion, the damping mechanism is storing energy in that spring and using it to return the knee back to its extended position, like a gait assist. Additionally, the second main purpose is that it prevents knee instability during the loading phase of gait. Loading phase is a biomechanical term. It's used to describe when the foot is coming down for the next step and is loading the weight of the patient onto it. And the damping mechanism then is providing a bit of energy to prevent that knee from being unstable when the patient is loading the knee. So then those are all the main sub-assemblies of the project. So I'm looking at the overall design and some of the properties of it. The weight of the entire knee assembly is 1.8 pounds, which is competitive compared to other knees on the market. It is primarily composed of stainless steel and aluminum. Stainless steel for the anterior and posterior bars, as you can see by the different colors here. And then aluminum for the rest of the design, mainly because the anterior and posterior bars are going to be maintaining most of the load throughout the design and thus need to be made of a stronger material. The cost for just a single prototype is about $3,000 right now, and then the range of motion again is 110 degrees. So with that, I'll turn the presentation over to Josh. We'll be discussing a bit more regarding what we've been doing in previous years on the project and kind of what we've been doing throughout this past year.
Thanks for time. So for about the past 2 years, we've been working on manufacturing a physical prototype of our prosthetic knee design. Starting in 2021, we began manufacture of the main body components, that is the bars and the platforms. And in 2022, we began manufacture of our sub-assemblies, that being the locking and damping mechanisms, starting with the damping mechanism. To manufacture all of these parts, we use the CNC mill machine and the lathe that we have in the shop here inside. You can see this image here is the CNC mill machine that we have in our shop. In order to produce the parts that we needed to make on this machine, we had to take our SolidWorks files and transform them into FeatureCam files, which can be read by the CNC machine, and it'll cut it out automatically. The other image on this slide is an example of one of the platforms that we manufactured using the mill machine. The other machine that we used is, or at least mainly, is the metal lathe, also in the shop. This was primarily used to manufacture cylindrical components. The component pictured here is one of the components for our damping mechanism. Unlike the CNC mill, the lathe had to be used mostly manually. So someone's at the machine and actually operating it for the full operation. Now I'm going to talk a little bit about what we did this past school year. We had three main goals. Firstly, after creating the main body components, we noticed there was a lot of friction in some of the joints. And so one of our goals this year was to introduce bushings to reduce that friction. Secondly, we wanted to finish manufacture of the damping and locking mechanisms so that finally we could fully assemble our prototype with connectors and all of the sub-assemblies. Here are the manufactured parts of our sub-assemblies. On the left, you can see the damping mechanism. You may notice that it is missing the yoke component that goes at the bottom. That part we actually outsourced in order to save ourselves time and because of how complex that part was. On the right, you can see the locking mechanism component. You may notice that we do not have the pin pictured here. That pin was bought commercially, so we did not manufacture that ourselves. When it came to reducing the friction in the joints, we decided that bronze bushings were the right choice. The specific type of bushing that we selected is called oil-like bushings, which basically means they have oil embedded in them. So as the bushings wear down, they continue to lubricate your joints, which makes them last long. Unfortunately, our initial main body design did not include bushings. So we had to resize some of the connectors and some of the holes in order to make the bushings fit. But here we have it, the fully completed prototype. I do have it here today. If you would like a closer look at this prototype, we will be out in the lobby right after this presentation. You can come and take a closer look at it. Let's talk a little bit about what our goals are moving forward into the next school year. Firstly, we want to complete physical testing on this prototype that we manufacture. Secondly, we want to create a user manual so that the people who need this prosthesis know how to use it and maintain it. And we also want to create a manufacturing guide. That way, whoever manufactures it, hopefully can manufacture it a little bit more efficiently than we did. And finally, some of our team members are going on a site team trip to Kenya this upcoming summer. We're hoping to receive some really good feedback and implement that. I'd like to take some time to acknowledge some of the people who have contributed to our project. We have Say Simu, Dr. Williams, Mr. Meyer, Mr. Shoemaker, Dr. Ferrer, Dr. Howell. And over here you can see we have an image of our current project team. Thank you all for coming. That's all we have. So do you have any questions?
I don't recall seeing what your cost target was. I saw what your cost estimate is and what your potential target would be.
Yeah, I can. So the question was, we saw what we expected as a cost estimate, but what do we expect the project to actually, or what do we expect?
What is Cure find as a target?
Correct. So what does Cure find as the target? So Cure's goal is going to be to have the knee cost the least amounts possible, or less than what their current commercial knees are going to be, which is around $2,000 to $2,500. Our cost estimate is an estimate right now because we manufacture most of these components in-house. None of this was externally manufactured. So for us, it didn't cost us really that much besides material costs. However, we have gotten some cost estimates from like if we outsourced all the components, and that was where the estimate of about $3,000 is coming from. This is going to be a bit of an excessive estimate because it's going to cost more money to make just a single prototype versus if you're buying them in bulk, which is what Cure would be doing. Say they have 100 patients who are going to need a through knee design, and they buy 100 knees up front. It's going to be a significant cost reduction. We're still working on getting that cost down by making improvements to a lot of like our machining processes, which would then bring down the cost and time to machine. But at this point, we're still at that $3,000 estimate.
Are there any other questions?
Talking in terms of manufacturing, so like, is the plan for Cure Kenya to outsource the manufacturing in Kenya or to them manufacturing themselves in Cure Kenya?
I believe the plan is for them to outsource the manufacturing. So I believe it will be done actually here in America and they will be shipped to Kenya. But reducing the manufacturing process, no matter where it's done, is a really important part of our design.
I think we're out of time now, so if there are no other questions right now, we'll be out in the lobby, but thank you all for coming.